We're going to get into the basics of probability. On this I've illustrated a sample space. I've used the letter U to denote what the name of the sample space is. Typically when we use a letter we are going to be talking about an event, which is a subset of the given sample space. Oftentimes you'll see this sort of symbol, an S with sort of a tail and a head, something like that, illustrating the sample space. Now that's typically done because, again, the events are letters, say A, B, C, different events that you pull different possibilities from the sample space. So this event A that I've labeled here, are the possible ways to achieve it are the values 2, 4, 6, and 8. So a probability, and this is the basic formula for all probability, we take the number of successes and divide it by n, which is the total amount in the sample space. So the number of successes that we've got possible for A are 4. There's 4 different ways to achieve A, so we have 4. And that's going to be divided by n, which we have 10 values, so 4 over 10. And that equals 0.4. So any value of this is going to have to be a value between 0 and 1. The probability of a certain event would be 1. The probability of an event that cannot happen, something along the lines of rolling the number 7 on a 6-sided die, would be a probability of 0. Any other probability must be a number between 0 and 1, inclusive. I mean, you can certainly be certain or impossible as well. Now, our fundamental counting principle helps us determine how many different possibilities we're going to have in our sample space when we're dealing with different types of things. So we use, again, the letter N for the total amount of one specific event, or one occurrence, and M being another one with a potentially different number. If M and N are the same values, then we use N times N. So for instance, if we're flipping a coin, there's 2 possibilities that we can get. We can get a head or a tail. If we're rolling a 6-sided die, there are 6 possibilities, 1, 2, 3, 4, 5, and 6. So the different ways that we can both flip a coin and roll a die, the different possible combinations, will be 2 times 6 or 12. So in this experiment here, I've set up a scenario where we have the birth of children. So the possibilities, if we're determining the sex, are either girls or boys. So G illustrating a girl has been born, and B illustrating a boy. So this is the possible number of ways that you can get girls or boys out of a family of 4, exactly 4 children. So I've broken it up into a distribution here. There's one way to get all 4 girls. Each one has to be a girl. There are 4 different ways to get 3 girls and 1 boy. So the boy is last, the boy is third, the boy is second, or the boy is first, and so forth. These are all the different possible combinations that we can get. Now we know that there will be 16 ways even beforehand using our fundamental counting principle. We have 2 to the 4th power, 2 times 2 times 2 times 2, and that will give us a value of 16. Now in blue here I've illustrated event exactly 2 girls, or 2 girls and 2 boys, whichever you prefer to write it as, and the number of possible ways that that can occur are 6. So the probability that we have exactly 2 girls is 6, which is the number of successful ways, divided by 16, which is n, which is the total number of ways possible. And the probability of that is 0.375. And again, this works pretty well because typically the probability of a girl versus a boy is roughly a coin toss, so about 0.5, and that's why this works.